Hello everyone. So in today's video, we are going to go over this paper and particularly the PEFT part of it, which is exploring versatile generative language model via parameter efficient transfer learning. So if you're not already familiar, I'm doing this series where I'm covering all the famous or commonly used PEFT works. So this is the third video in the series, and let's delve right into it. So, what's the core idea here? The problem is very similar to what we've seen before. Fine-tuning pre-trained language models to downstream tasks is very good. It gives very good results. But then you have a new model for each and every task, which is not very ideal for scenarios where you do not have enough memory or enough compute to run all of them in parallel or to swap between models efficiently. So the solution which people have been using at this point, so this paper is from 2020, it was to have a parameter sharing schema. So you fix the parameters in the base model to some degree, and then you only fine tune a set of parameters, which are these task specific parameters, which are specific to specific data sets. And then when you want to do, say, machine translation, you plug in those parameters. When you want to do summarization, you plug in a different set of parameters to get your model ready. Now, what's the high level setup in this paper? So first of all, they introduced something called as a versatile language model, which is very similar to a transformer model with very subtle differences. So they take a pre-trained backbone like GPT-2 in their case, and then they introduce two kinds of specialized parameters. One is these low rank residual adapters, which is same as the adapters I've covered in the previous two videos or the adapters you might be familiar with in general. And then they also have this task embeddings. So let me just go over both of them as we like cover them. So the design of the adapter is similar to that in this Bapna and Firat paper. So the original adapter paper, it also tuned these layer norm parameters. However, in this subsequent paper, they realized that they could just avoid tuning the layer norm parameters of the original transformer and instead have a layer norm inside their adapter structure. So this is what this paper did, and it was a very competitive adapter architecture. You can look it up. I also covered this in my last video, so I won't go over the architecture details again. But as for the formulation, you can see that we get this hidden representation which is generated before the adapter by the normal processing of the transformer. The adapter first applies a layer norm. Then there is a MLP. So first you have this down projection, then you have this ReLU activation, and then you have this up projection. And then due to the residual connection, you also add the hidden state from before. So this is how your adapter looks like. And then you can see that these adapters are present inside every transformer layer. So this is the adapter part. And then they also have this task embeddings. So they want to adapt these language models to different tasks which have some conditional behavior. So for instance, for summarization, you have a document and then you want to generate a summary, or for question answering, you might have a bunch of questions beforehand. So they want to denote this somehow to the model. So for this, they create these task embeddings. And these task embeddings are basically embeddings of things like, say, article summary or source language, target language, to introduce these kinds of things. And since you know at the very first stage, the transformer first embeds the tokens into embeddings and then adds this positional information. They also add this segment embeddings at the very same time. So I can show some of these. Uh, if you so this is their code base. So you can see that these are some tokens. For instance, source empty is one token, question is one token. So some, for instance, if your text has a question and then an answer, then for each token which belongs to the question, you will add this embedding for this special token. And now you might be wondering, how won't this be tokenized in some special way. So they add this to the vocabulary. So I hope this is clear. You can also look at their implementation for more details. The repository is just VGLM. Now let me just go full screen again. Right. Now, and the final thing which to do is just knowledge distillation. So this is from a prior work where you this work by Kim and Rush where they use sentence level knowledge distillation. So at a very high level, their idea is that the model's output distribution can be very different from what the data set is. So maybe the model writes more like an old person while the data set was created by a bunch of young people. Just an example. So what they do is they first fully fine tune a GPT-2 model on the training task. So for instance, machine translation on summarization. Then they replace the gold labels, which is the original labels which they have in the data set, with the greedy decoded output from the full fine-tuned model. So now, for instance, you have a sentence and it's translated golden label. Instead of training on that golden label to get signal for back propagation, you will now use the generation from a different fully fine-tuned GPT-2 model. And this is how they construct a new training set, which is used to fine-tune the student uh, versatile language model. So I hope all these points are clear. Now we look at some setups which are shown in the paper. For instance, this is a task where you have document, then you have some tokens for a question, then you have an answer, then you have some tokens for another question, and then you have an answer. So if you look at this, the document is hero Ada is 20, and then question one is who is hero? The answer is Ada. Then the question is how old is she? And then the answer is 20. So you can see that in this case, the task embeddings relate to this CQA task. So we'll go over the task names later. But I hope this is clear. Similarly, you have this where you have different attributes. So for instance, you have attribute one, which is name eagle, then attribute two type Italian. And then you can see in some cases, like the word Italian gets split across tokens. Then you have attached the segment embedding to both of them. Then area is center. And then the response is the eagle is an Italian restaurant. So I uh, hope this is clear. This is a translation task from, I think, German to English, and then this is a dialogue task. So you can pause and look at the example if you want, but I'll just move ahead since I think this is plenty. Now, the data sets they use are these five data sets. So DLG is a dialogue data set, and then for NMT, which is neural machine translation, they use this German to English. For summarization, which they call SUM, they use CNN Daily Mail text summarization. For conversational question answering, they use the COCA dataset. And then for natural language generation, they use the end-to-end NLC challenge. As for the model, they use GPT-2 small, which is 124 million parameters. This might seem very small by today's standards, but please remember this was 4 years ago. And now the adapter bottleneck dimension, they experiment with all of these sizes, and then they choose these particular sizes for these corresponding data sets. So if you want to maybe run these experiments, this might be a good place to pick the hyperparameters. Now, the final slide, we'll just go over the results. So again, the intention of the series is to make you comfortable with the methods themselves. And I'm just showing the results to for completeness sake, but the results is not something which I'm especially focused about. So there are a lot more things mentioned in the paper, which I'm not covering. And to sort of get an idea about those, it would be worth reading the paper. So let's go over this point by point. The first one being fine tuning, only the adapter is introduces 13% additional parameters. When compared to full fine tuning, you get 100% additional parameters. And then the loss in performance is only 0.4% compared to fine tuning a full GPT-2 model. And then the adaptive layers are more effective both in terms of performance and the number of additional parameters compared to fine tuning only the language model head. So you can see the language model head introduces 2.55 times additional parameters, while this visual language model only introduces 1.13 times. Uh, so basically, this 13%. While for the full fine tune, you get this 5x behavior. Now, these two plots are specifically for the summarization and the machine translation datasets. So you can see the top line is full fine tune, while this bottom line is the language modeling head accuracy. So since you only go up to 4% here in the ratio of parameters, while these use significantly larger, so they are omitted. So did uh, you do not see them as like uh, at some place with their parameter ratio because they have a fixed parameter ratio, while for other things you can tune the parameter ratio by tuning the adapter size. So the simple VLM is this red line, and then when you add distillation, you can see that it performs better. So if you're wondering why distillation, this is why distillation, and similarly for this as well. And you can see by the end, when you are only like 4.5%, using 4.5% parameters, you're already very close to full fine tuning in both cases. So this might seem off to you, but you can see that this is 18.1 versus something like 17.6, so very close again. Now, using knowledge distillation is very useful, especially for NMT and sum, where you can see these green lines go up. This is because the gap between fine-tuning the whole model and the adapter is large, and knowledge distillation reduces the complexity of training target because you're replacing the gold label by a teacher model generated target, and this provides an easier label for summarization and translation. Now, are the task embeddings useful? Yes, they are. So they are very useful for achieving competitive performance independently of the adapter. So even if you remove the task embeddings while keeping the adapters, you see that the perplexity goes up, the blue goes down significantly, the rouge goes down, F1 goes down significantly, and so on. So this is because all these tasks have a very nuanced structure. So maybe document first and question then answer. And without the task embedding, it becomes difficult for the model to distinguish between different parts of the question. And now finally, the visual language model can be trained in two ways. One is where you freeze the weights of the GPT-2 model and then independently and continually learn one task at a time. So you get multiple different tasks learned one after the other. Or you can do multitasking and then fine tune both the model and the adapters. So both of them are viable options. So in the second option, you get this benefit of being able to do knowledge transfer between tasks. So if two tasks are, say, very close question answering and say, for instance, chatting, which also has a lot of question answering at times, then you will be able to transfer knowledge between tasks. So VLM with multitask, which is this right here, and it gets the one of the best perplexities, and the F1 score also improves by 3%. On the other hand, if you use sequential learning, you have the benefit of having a base model which is unchanged, and then you can just bring in adapters uh, as you wish. So that has also a bunch of benefits in itself, and then you can weigh and trade off based on your use case and utility. So this was the last slide I had, and I hope this paper is now very clear. I'll be covering, I think, a few more adapter papers before moving on to more recent methods. So this entire playlist serves as a literature survey of some sort as well. If you have any paper suggestions, feel free to leave a comment down below. And thank you for watching.